Hello, welcome to Dr. Nakamura's lecture series on bridge engineering, number A-9. Chapter 11, Suspension Bridges. This is the Severn Bridge built in 1966 UK. This is the innovative suspension bridge which adopted the streamlined box girder with the inclined hangers. I studied this bridge for my PhD at Imperial College London in 1985. The boy in this photo is my son, who is now a grown-up man. The Akashi Kaikyo Bridge, the world's longest suspension bridge. Nippon Steel Corporation was the producer and contractor of the cable work, for which I was the deputy project manager. This is the Hammersmith Bridge in London, built in 1887. In these days, the chains composed of wrought iron bars were used. This is the chain bridge in Budapest, built in 1849. The bridges light up at night. It's a classical and beautiful bridge. This is the Brooklyn Bridge in New York City, the first modern suspension bridge with cables. It was built in 1883, the span length of 483 meters. This is the Millennium Bridge in London, a suspension bridge with very shallow cables. It's more like a suspended slab bridge. It was opened in June 2000, but the lateral vibration was induced by pedestrians. This bridge had a similar problem. I clarified the vibration mechanism and published a paper, which was conferred the Henry Adams Award by Institution of Structural Engineers. 11.2 Structural form of suspension bridge. The suspension bridge consists of 5 elements: girder, main girder, hanger, tower, and anchorage. The girder is lifted up by the cable through the hangers. The cable goes up to the top of the tower and rested to the anchorage. The cable saddles smoothly support the main cables at the tower top and the anchorage. The anchor frames are embedded into the concrete of the anchorage. Let me explain the mechanism of force transfer in the bridge elements. The dead and live loads work on the girder, and the girder is lifted up by the hangers, which are connected to the main cable. The main cable goes up to the tower top and then is fixed to the anchorage. 3. Stiffening girders. The girder resists vertical and lateral forces such as winds. For long-span suspension bridges, most of the dead load are taken mainly by the main cables. Therefore, the girder does not contribute in this regard, and it can be a very small section. However, the bridge may become unstable due to strong winds if the girder is very flexible. Therefore, the girder needs necessary bending and torsional rigidity. The truss girder or the streamlined box girder are usually adopted for modern suspension bridges. A is the Golden Gate Bridge with the truss girder. B is the Swan Bridge with the streamlined box girder. 4. Tower. The main cables are supported at the tower top, which causes the axial compressive force into the tower. Winds or earthquakes cause the bending moments in the tower. The steel towers are favored for modern long-span suspension bridges. It is designed to satisfy the buckling strength for the axial compression and the bending strength for the lateral forces. There are basically three structural forms. The two columns are connected by trusses in A. They are rigidly connected by cross beams in B, and they are connected by trusses and beams in C. This is the tower of the Akashi-Kaikyo Bridge. These show the examples of A. rigid frame type and B. the truss type tower. 5. Main cables. The strand consisting of helical wires are used for the cables on short and medium span bridges, whereas the parallel wire strands PWS are exclusively used for cables of long span suspension bridges. The photo shows the cable model of the Golden Gate Bridge. The main cable consists of galvanized steel wires, and its diameter is about 5 mm. Its tensile strength was 1100 MPa for the Brooklyn Bridge. That of the Akashi-Kaikyo Bridge is 1770 MPa. The wire of the under construction Chanakare Bridge will be 1960 MPa. Here is the information of the cables of the Akashi-Kaikyo Bridge. The main cable consists of 290 prefabricated parallel wire strands. Each strand consists of 127 galvanized steel wires which are bundled in parallel. Total number of wires is 36,830. A galvanized wire is 5.23 mm in diameter with the tensile strength of 1770 MPa. The strands were fabricated at the factory and transported to construction site. The strand was wound on the reel as shown here. It weighs 85 tons. This shows the strand was spread on the working floor, which is called catwalk, and placed into the final position of the cable. The strands were set on the tower saddles at the planned positions so that all the strands were set in parallel. After all the strands were installed, they were compacted to form a circular shape. Then the cable bands were installed around the cable, to which hangers were attached. This is a suspension footbridge with a main span length of 320 meters. The spiral strand consisting of helical wires are used for cables on short and medium span bridges. 6. Hanger ropes. Hanger ropes connect the girder and the main cables. The hangers were connected to the cable by the cable bands. This is one of the examples of the connected detail. 7. Anchor frames and anchorage. The cable is spread at the spray saddle on the front part of the anchorage. The cable is fixed to the anchor frame in the back part of the anchorage. The anchorage is a concrete structure to resist huge cable tension. The anchor frame is made of steel members and embedded in the concrete. This shows a detail of socket attachment to the anchor frame. That's all for this lecture. See you next lecture.